All right, everybody. So we're going to go ahead and finish up the solutions to the practice test for exam 3. We left off at problem 8, and I'm just going to do them in the same set of notes, but obviously there are 2 videos for it now. So I was smart enough to draw some of the graphs, so that will save us some time, and we will go ahead and get started. So on problem 9, we're given these 2 graphs right here, and what we're supposed to do is determine if they are isomorphic. So this is actually the same as problem 8, but the graphs are different. Um, yeah, let me write that. Determine if the graphs are isomorphic. And our strategy is the same as before. You know, you count up the vertices, you count up the edges, and then you start looking at more complicated things that should be the same between the graphs, but may not be. So we'll do it exactly the way we did the previous one. So first, count up the number of verts, right? So count the vertices, 1, 2, 3, 4, 5. So that's 5 on the first graph. On the second graph, obviously 1, 2, 3, 4, 5, also 5. So it's 5 and 5. Okay, so count up the number of edges. Actually, I'm going to skip that, and instead I'm going to go to the degree sequences. And the reason I'm going to do that is because, as we saw in the previous video, counting edges is hard for me, but the degree sequence is easy because you just look at one edge at a time, or sorry, one vertex at a time. So let's just write the degree of each vertex next to each vertex. So we got 3 here, 1, 2, 3, 4 here, 1, 2 here, 1, 2, 3, 4 here, 1, 2, 3 here. Do the same thing for the other one. We got a 3, we got a 2, 1, 2, 3, 4, we got a 4, 1, 2, 3, we got a 3, 1, 2, 3, 4. So we got a 4. All right. And if you look at these, so I'll put them in ascending order. For the first graph, we have a 2, then we've got 2 3s and 2 4s, right? So that's the first graph. And for the second graph, we have a 2, 2 3s, and 2 4s, right? So they're the same, right? So same. Now that does not necessarily mean they're isomorphic. You have to look in more detail. So after we do that, then you want to ask yourself questions. Like if you take a look at a degree for vertex, for example, um, well, I said degree 4, so we'll do degree 4. If you look at this degree 4 vertex, right, U2, you can see that that degree 4 vertex is adjacent to a degree 3 vertex, a degree 3 vertex, a degree 4 vertex, and a degree 2 vertex, right? Um, so then you say, well, is that going to be the same over here? So there's 2 of them here, but let's before we do that, let's look at this degree 4 vertex. This degree 4 is adjacent to a degree 2, a degree 4, a degree 3, a degree 3. Okay. Now over here, if you try to compare that, say this degree 4 is adjacent to 3, 2, 4, 3. Okay. That seems the same. Or at least I don't notice that it's different right away. This 4 is adjacent to a 2, a 3, a 3, and a 4. That seems, again, I don't notice anything wrong with that off the top of my head. I could write them down if I think that they're different. So let's say here. I know there's got to be something different here. Well, I guess I don't know, but I suspect that there's something wrong here. Here's what I suspect is wrong, or here's what I notice is wrong. So take a look at this edge right here and this edge right here. If we think about just taking this vertex 2, and instead of drawing it right here, imagine I moved it over here to this side of the graph. So I'm going to draw it in a different color here. So let's like light green. So let's say that I moved V2 over here, and then I drew it here. So I connect that, and then I go like that. That's where V2 is connected. And then if I erase it here so we can get a better look at it, and you look at these 2 graphs, and now they do seem different because um, if you look here, you've got these two, you have like a 4 to a 4 to a 2 to a 4. And here you have a 4 to the 2, okay, to the 4. I guess that's actually doesn't seem wrong. Um, but it does look different, right? It doesn't feel different. Um, that there's this here, where here it goes, um, this structure where you have the 2 connected to 2 4s, and then there's 2 vertices between the 4s. But maybe it's not, because maybe we're just looking at it in the wrong shape. So it feels like they're not isomorphic, but we haven't shown that they're not isomorphic. Okay, and that's important to understand that just because everything we've checked so far seems like they're isomorphic doesn't mean they're actually isomorphic. And these problems can be pretty tough. So I'm stalling for time while I look up the um, my old solutions so I don't have to think. um, let's see here. Where are we? 9. We're on 9. They are isomorphic. Bum bum bum. Okay. Um, yeah, which makes sense because, like I said, it feels like they're not because it looks like they're different, but there's supposed to be a mapping that shows that they are. So let me back this up and let's try to find the isomorphism. So far we've failed to show that they're not isomorphic, right? Because that's what we were trying to do, is show that they're not, and we haven't. I'm just rearranging this a little bit. These are the degree sequences. Okay, so seems isomorphic. Also, I realized that we didn't count the number of edges, but we don't really need to count the number of edges, because if the degree sequences are the same, like they are, and you know that the degree sequence is related to the number of edges, right? Like add these up and it's 2 times the number of edges. Well, if these are the same for each graph, then they must have the same number of edges. I don't need to count the number of edges. So I'm just going to erase that. So what's the punchline so far? So what we've done so far is we looked at a few things, degree sequences and so on, and we failed to show that it's not isomorphic. So it may be isomorphic. So if it may be isomorphic, what you try to do is you try to show what vertex is equivalent to what vertex. So here's how you would do that. So you try to come up with the isomorphism. So try to find the isomorphism. Now the problem doesn't say to do that, okay? But the only way to know for sure that it's isomorphic is if you can do this, okay? So what we want to do is map the vertices from one to the other. So the vertices on the first graph are called U1, U2, U3, U4, U5, okay? And then what we want to do is we want to make sure, or not make sure, we want to map them to vertices on the second graph. And we need to map them to the vertices that they're like. Okay, so you come up here and you say, like, what's the easiest one to start with? Is probably U3. The reason U3 is the easiest is because it's the only degree 2 vertex, right? So the only degree 2 vertex on the left must be the only degree 2 vertex on the right. So U3 must correspond to V2. So we go over here and say U3 must correspond to V2. Okay, so we did that one. So we did that. Move on to the next one. So from there, you can say, okay, well, U3 is adjacent to 2 degree 4 vertices. And there doesn't really seem to be any difference between these two, right? Like if I drew this graph a little bit different, right? I put the U3 up here, for example. I haven't really changed the graph, right? I shouldn't do that. The graph as it was originally drawn is the graph, but I'm just redrawing it like this. At this point, the graph is perfectly symmetrical, right? So this vertex is connected to these two, and there seems to be no difference between them. And over here, V2 is also adjacent to 2 degree 4 vertices. And if this is correct, then maybe there's no difference between these either. So one of these two, the V5 and the V3, must be U2 and U4, and I don't think it matters which. So let's just write those down. So let's just say the U2 is equivalent to the V5. U2, V5. Okay. And then the other one, so we did that. Hey, I wasn't trying to erase, I was trying to cross out. And then so the other degree 4 vertex, V3, must be the same as U4. All right, so we did that. And then you have to check that you're doing what we call preserving the edges, which means that if there's an edge between vertices over here, there must be an edge between the vertices over here. So like, for example, the U2 and the U4 are supposed to be adjacent to each other, right? The 2 degree 4 vertices are adjacent to each other. So you check over here, are the 2 degree 4 vertices adjacent to each other? Yes. So far, like this little triangle that these make corresponds to this triangle over here that this makes. So this seems okay so far. Okay, so far, so good. So let's continue on. From there, we get that one of these degree 4 vertices, the U2, we already know that it's adjacent to these other two that we've already picked. It's also supposed to be adjacent to the U1 and the U5, right? So U2 is supposed to be adjacent to U1 and U5. So over here, what was U2? U2 was V5. So V5, it should be adjacent to 2 other vertices. Actually, sorry, let's back this up. U2, since it has degree 4, it's actually adjacent to every other vertex, right? And same thing here. This U4 is adjacent to every other vertex. And this V5 is adjacent to every other vertex. And this V3 is adjacent to every other vertex. So I don't think we have to think very hard about this. I think we can just kind of fill these in however we want. So let's just say that the U2 is also adjacent to U1 and U5. And the equivalents to that over here are the ones that we haven't crossed out. V5 is adjacent to V1 and V4. So let's just say V1 and V4, because we got to fill them out somehow. And let's say that's how our isomorphism is going to work. All right. And once you've done that, then we're done. As long as you're sure that every edge over here between 2 vertices corresponds to an edge over here between 2 vertices. Right, so I'll just say one thing about that and then we'll be done with this problem. All right. So if you take any edge here, you can do this for all of the edges. But like if you look at an edge here, like let's say you look at this edge, U1 to U4, right? So U1 is adjacent to U4. Actually, that's the way to write it. U1, U4. Okay. Now, from the mapping down here, U1 is supposed to be V1, and U4 is supposed to be V3. And that's a question. Is there an edge between V1 and V3? So you come over here and say V1 is here, V3 is here. Yes, there's an edge there, right? So that edge is in both graphs, U1 to U4 and V1 to V3. Okay, and that's 1 out of the 7. And if you check all 7, is there 7? I don't know. 5, 8, 12, 16. No, there's 8 edges. So there's 8 edges. So if you check that every edge over here you write it in terms of u, and then you write the mapping, the mapped vertices here, and then you check that that's actually an edge over in the second graph, and it is for all 8 edges, then this is in fact an isomorphism, and that means obviously that they're isomorphic. Okay, so that's a lot of words, but yes, they are isomorphic. Okay, and they're usually not this hard to solve. You normally don't need to come up with the isomorphism. It's normally kind of obvious that they are or that they aren't. Okay, so let's look at the next one. Again, the question is, are they isomorphic? Isomorphic. And I think this one's easier to see because this over here is obviously just a cycle that goes U1, U2, U3, U4, U5, U6, U7. And if you trace this around, it does the same thing. It just goes V1, V3, V5, V7, V2, V4, V6, back to V1, right? But you still, it's just a big cycle. It goes, starts at V1 and goes all the way around this graph and comes back to V1, just like this does, just drawn a little bit different. So if you wanna come up with the isomorphism, you don't have to do as much work as what we did on the previous problem, right? Like you can just say, this is V1, for example, and then V1 goes to V3. So this must be V3. And then U2 goes to U3, V3 goes to V5, so this must be V5, which goes to V7, so this must be V7. V7 goes to V2, so this must be V2. V2 goes to V4, so this must be V4. V4 goes to V6, so this must be V6. V6 goes back to V1, and here, that's correct. Goes back to V1, which is U1. So doing that, essentially what we did here was we just drew the isomorphism, and we didn't write it like this. We just wrote on one of the graphs what the vertices map to. But that is the isomorphism. So yes, isomorphic. Okay, and that's really all there is to it. It's just, are these graphs the same but drawn differently? And so if you can figure out which vertex in one graph is which vertex in the second graph, then you've done it. You've found the isomorphism. Okay, so let us open my practice problems again. So we're on problem 11 now. So, 11's got a picture as well that I didn't draw. So let's draw it. So got this, you get this. This is water. Hold on. This is water. No, that's the opposite of where the water is. This is water. Wait, that makes more sense. Okay, and then over these bridge, or over the water, there are bridges, and so there's a bridge here, bridge, 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 and bridge. Okay, so what, like there's a river, there's some islands, and there are some bridges. And the question is, can you cross all bridges exactly once and end up where you start. Okay. And you can try it like just before we solve this with graph theory. You can solve the, or you can try to solve this just by trying it. So like you can just pick somewhere to start, and you can say like, okay, we're gonna start here, and then just say, okay, well we go across that, go here, go here, go here, go here. Um, yes, yes you can, right? Um, so it looks like that is doable. Yes. Um, we were supposed to do it with graph theory though, so let's do it with graph theory. So if you do this with graph theory, every piece of land is, oops, there we go. If you do it with graph theory, every piece of land is a vertex. So like this side is a vertex, call it A. Um, this could be B, this could be C, and this could be D, and that's it. There's only four sides. Um, so then if you draw the graph, you go vertex A, vertex B. It helps to draw them in pretty much the location where they appear in the graph. Um, and then you draw an edge for every bridge. So like this bridge is A to B. That's that. Here, this is a bridge from B to D. This is a bridge from B to D. Two bridges B to D. So you draw two. This is from B to C, B to C. This one's C to D, C to D. And then we have this one, which is A to D. And that's all the bridges, I think. So you draw it that way. And then the question is the same as can you cross all bridges exactly once and end up where you start um, is there an Euler circuit on this graph? Okay. And we already drew it, so yes. But the answer comes from a theorem. The theorem says Euler circuit exists if and only if the degree of every vertex is even. And there's an Euler path exists if and only if, well, not if and only if exactly two vertices have odd degree. So if two of them have odd degree, then one of them is your starting vertex and one of them is your ending vertex. And then you can go through all the other edges, but you can't make a whole cycle. So, okay, so that's your theorem. So if you just write the degrees again next to all these vertices, 2, 2, 1, 2, 3, 4, 4, 1, 2, 3, 4, 4, right? So they're all even, right? So in this case, all degrees are even. So yes, you can. Or yes, there is an Euler circuit. And therefore, the answer to the question, can you cross all the bridges and get back to where you start, is yes. So cross all bridges once and end up where you start. And we did it, right? So we even drew it on the graph already. I think we started here, in A and we did this. Easy. Now, if you drew that, if you drew it and said that's why you can do it, then that would have been fine for an answer. You don't have to use the graph theory in that case if you can actually demonstrate what's going on. All right. 12 says, can you draw the pictures with a pencil and without retracing or lifting your pen? So for example, right, like here's a picture that you can draw without lifting your pen, right? Because I just did it without lifting my pen. And the point is that when I drew it, first of all, I started here, I ended here, right? Because I went like this. And I did not end where I started. So this has nothing to do with an Euler circuit, because a circuit means you end up where you start. But it does have to do with an Euler path, because you start in one vertex, you go around the graph, tracing every edge, because every edge is a line in the drawing, and then you end up somewhere. But the somewhere doesn't have to be where you start. So what we're going to be doing in this case is we're going to be looking for an Euler path. Now, technically, an Euler circuit is an Euler path. So I said Euler path exists if exactly two vertices have odd degree, but also if none of them have odd degree, because then you have an Euler circuit, which is an Euler path. So this is not the drawing, of course, that we're supposed to check, but we have some. So I think the first one looks like this. I did not draw it without lifting my pen. And then, but that doesn't mean you can't. That just means I didn't. And the second graph looks like this. And so here's how you do this. Essentially what you do is at every single point where the lines cross, put a vertex, right? Because there are no vertices. So you put one here. So every place where they cross, and that's kind of the key. You have to put one here, but like, don't just do this. Because if you just do this, then the answer would be no, because if you think about it, you go from here to here to here to here, you've traced this part of the graph, but you haven't even drawn the other half of the graph, right? Um, but if you put a vertex where at every time the lines cross, like this, now what you can do is when you're drawing it, you can think of start here, go here, and you can make a turn at these corners now, right? Like when you get here, you have choice. 4 places you can go from here. Whereas before, you couldn't do that, right? Where you could only draw that triangle or you could draw that triangle. Now you can go from this triangle, you can go here, 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 and then take a turn and then draw the other triangle. So that's what you want to do is everywhere they cross, draw a vertex. Or sorry, yeah. So basically, draw a vertex at every every time, every place lines cross. Then what you want to do is check the degree of each vertex, just like we did on the previous problem. Check degree of vertices. And then if all even or too odd, then you can draw it without lifting your pen. Right. And then my stupid little drawing looked like this or something. Um, if you count up, if you follow my strategy here, first of all, you can obviously draw this without lifting your pen because I did. And if you write the degree of every vertex, like 1, 2, 3, 2, 2, 2, right? You can see that in this case, there was an odd degree and an odd degree, and the rest are even. So that's what happens if you start at one vertex and stop at another vertex, then you end up with odd degrees, but only on those two. So that's the way it goes. So this is the method. So you just count up all the degrees now, and this answer will be easy to find. So you just go 2, 2, 2, 2, 2, 2. And then the inside ones are 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they're all even. So yes, for that one. Then we have to do the same thing over here. Again, every place that the lines cross needs to have a vertex. So here, 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 here. Also, I guess where you start and where you stop also needs to. Actually, technically, by the way, you don't need to put them at the corner, right? Because you can just think of this as being one line. This is one edge if you want to think of it that way. Um, so you don't have to put in corners. But if you do, it's no big deal. All right, so let's put the degrees next to all these. So 1, come on, 1. This is what, 1, 2, 3, 4. My drawing's so bad I can't do it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1. So that one has two odds. So the answer is also yes. Easy. And if you put in the corners, right? Like if you add those corners in, the corners are just going to be degree 2. So they'll be fine as well for all the corners of that box. All right. So that one's easy. That was problem 12. We're on to problem 13. Drawing graphs. Draw graphs. A is C5. C5 is a cycle with 5 vertices. So 1, 2, 3, 4, 5. Done. B is W6. So I think W is the wheel, and it has one more vertex than it seems like it should have. So W6 is C6. So 6 vertices, 1, 2, 3, 4, 5, 6, and then an extra one in the middle. So 7. So 6 around the circle, and then a central one, and the central one is connected to all the others. So there you go. I think that's the umbrella logo. C is K4. K4, that's the complete graph with 4 vertices. So 1, 2, 3, 4, and then every edge is connected to every other edge. So like that. D is Q3. Q3 is the three-dimensional cube, which there's a way to there's a method, right? Here, I'm gonna just put these vertices in. So three-dimensional cube, you draw 2 squares and then connect the corners like that, and that's Q3. The definition of Q3 actually comes from 3-bit binary numbers, where if you label every vertex on here with a binary number, so like 0, 0, 0, 0, 1, 0, for example, 1, 0, 0, for example, 1, 1, 0, then there should be an edge between every between edge, there's an edge between vertices if they differ in one place. So like 1 0 0 1 1 0, they differ in the middle digit, so there's an edge. These differ in the first digit, so there's an edge. These differ in the second digit, so there's an edge. These differ in the first digit, and there's an edge. And then the last digit's 0 on all of them. So the square behind it are the same numberings, but then the last digit is a 1. So like 1 0 1, because this is 1 0 0. So back here it's 1 0 1, 1 1 0. So this is going to be 1 1 1. 0 1 0. So this one back here will be 0 1 1. We're just changing the last digit to a 1. And 0 0 0 will be 0 0 1. And so I think that'll work. But, it's a lot easier just to draw it because you know what it looks like rather than that. Also, I draw Q2, Q3, and Q4 in the lecture on whatever it is, 10.2, 10.3, something like that. Are we done? Oh, no, we're done. No more. Okay. 14. Problem 14. Okay, finally, finite state machines. Yay. So on problem 14, which you did not have homework on, which is what makes it hard, well, it's not really hard. You'll just have to watch the lecture if you didn't, or just pay attention to this, and should work okay. So let's see here. So I've got to draw this. We have a state. I need to move this already. I'm down here. State, 3 lines. F, input, 0, 1. G, input, 0, 1. So we're going to draw state table here. So we have 4 states, S0, S1, S2, S3. Then here we have S1, S0, 0, 0, S2, S0, 1, 1, S0, S3, 0, 1, S1, S2, 1, 0. Okay, so what this is this is a state table for a finite state machine. And then the questions are just going to be basically, do we know how to read this? So like part A says, if the current state is S1 and the input is 0, what we want to know is what is the next state and what is the output. Okay, so what you have to do here is this. It's not that bad. So the current state is S1 and the input is 0. So where that is on the table is the current state is S1. So that means we're in the row that starts S1. So this row. Okay. Let me erase this. Put a different color there. Put like light green. Now the input is 0. And you'll notice that this is labeled input and this is also labeled input. So this is input 0 and this is input 0. So there's 2 columns labeled input 0. So one column is here and the other one is over here. And the reason there's 2 columns is because one of these columns is going to give you the next state and one of them is going to give you the output. So what you've got is this is going to be your next state and this is going to be your output where those intersect. So the next state is going to be S2 and the output is going to be 1. All right, so that's pretty straightforward. B is very much the same problem. So let's just duplicate this. change the numbers. B. Erase. That. All right. So we're going to do this again. So I have to erase all my pretty coloring. And we'll do this again. So on B, current state is S3. And the input is 0 again. So we'll do this just the way we did the last one. So the input is 0. And the current state is S3. So you come up here and say current state S3. So we're in the S3 row there. The input is 0. So we know that there's two columns corresponding to input 0, one here and one here. And just like before, where those intersect, those are the numbers we need to read for the next state and for the output. So the next state is S1, and the output is going to be 1. Right? So that's not actually that hard to do, especially if you have like a highlighter like we just had. And that's how you read that. So let's go. Now, the next thing is we have to draw the state diagram. Draw the diagram. And the diagram represents the same exact information here, but in a drawing instead of a table. So what you do is you put your 4 states, S0 to S3, as circles here. Oops. S0, S1, S2, S3, and then each row of the table is an arrow, basically. 2 arrows, actually. So coming back up here, let's, well, no, I want to leave the colors on here. So let's start at the beginning. So you're in state 0. So you're here, state 0. And you, from state 0, you could either move to S1 or to S0, right? These are your 2 choices. So from S0, you either go to S1 or S0, which is staying where you are. So you draw arrows from S0 to S1 and S0 to S0, S0 to S1, and also S0 to S0. All right. So that takes care of this part. Now you have to worry about this part. So what this is going to say, the input is up here. So this is input 0, output 0. Input 0, output 0. And that's on the first one. So like the first column. So on the S0 to S1 line is input 0, output 0. So you put a 0, 0 there. Now, the second one here, S0 to S0, you go S0 to S0 if the input is 1, right? This is input 1. We go to S0. So the equivalent in this column is input 1, output 0. Input 1, output 0. So on the line that goes from S0 to S0, you put input 1, output 0, which is 1, 0. Okay, so each row of the table is 2 lines. And then we do it for every row. So S1 to S2 and S1 to S0. 1 to 2, 1 to 0. So we can go 1 to 2 or 1 back to 0. Those are the 2 choices. Now it's input 0, right? S1 to S2 is input 0. So input 0, output 1. So 0, 1 corresponds to this entry. 0, 1 on the arrow that goes to S2. The other one is 1, input 1, output 1. So 1, 1 on the other one. All right, half done. Next row, S2 row. So S2 can go to S0 or to S3. So S2, S0, S2, S3. 0 and 3. So 0 or 3. Okay. Now, how do we label them? So first one here was input 0. So the one that goes S2 to S0 is input 0, output 0. So input 0, output 0. So 0, 0 on the one that goes to 0. The other one goes to S3, and that's input 1, output 1. And that's it for that row. Last row. So we've got S3 can go to S1 or S2, 1 or 2, 3 to 1, 3 to 2. So 3 to 2, 3 to 1, like that. Those are your choices. You go to 1 when the input is 0 and the output is 1. 0, 1 on the one that goes to 1. You go to S2, second column here, when the input is 1 and the output is 0. So 1, 0 on the other one. All right. So every pair of numbers is the input and the output. And that is your diagram. And we're done with that one. So again, there's a whole lecture on that if you want it. So you can find that and look at it if these are complicated for you because you didn't do homework. All right, 15. So 15 is basically the same problem, but they give you the diagram instead of the table. So we got S0, S1, S2, S3. Probably going to shrink this. Maybe I won't, I don't know. We have that, and this is 0, 1. This is 0, 1. This is 0, 1. This is 1, 0. 0, 0. 1, 1. 1, 0. 1, 0. I think that's it. So they also say start. They also label this as start. But by convention, S0 is the start. So it doesn't really matter if you have that. All right. So there you go. There is your state diagram this time instead of a table. And we're solving the same basic type of problem. So A says if the current state is S1 and the input is 1, we want the next state and the output. So just like the previous problem, next state, output. All right. I think maybe these are easier to read for this. So if the current state is S1, you're right here, right? And there's two arrows leaving, S1, this one, and this one. So this one is labeled 0, 1, and this one is labeled 1, 0. So the first digit is the input. So if the input is 1, then this is the correct arrow because this has input 1, this is input 0. So this arrow, and if you follow this arrow, then input 1, output 0. So that would tell you the output is 0. And also, you're going from here to here, so the next state is S3. Right? So you're looking for the 1. Ooh, that's not what I wanted. Right, so the input is 1, That's here. So that's how you know what arrow you're on. And then you just read off the output and the next state. Right? So the output's there, which is right there. And obviously you end up in S3, which is right there. Okay, so that's kind of easy to do. B is going to be, again, the same kind of deal. So I'll duplicate this and erase. All right. So on B, it says we're in S3 and the input is 0. So this time, we're starting in S3, right? So we're starting in S3. So we're starting in S3. The input is 0. So there must be 2 arrows leaving here, one here and one here. The input is 0, right? So we're looking for the one with input 0, which is this one. There's input 0. So then we just need to read off the other numbers. So obviously the output is going to be a 1, and we're going to end up there if we follow that arrow. So what's that tell us? It tells us that we end up in S1, and it tells us that our output is 1. Easy peasy. All right. Last problem of the whole test. C. So we got to draw the table. Okay. So to draw the state table, I am going to save us a little bit of time. Duplicate this table. Bring it down here. We have to erase a lot of it though. All the insides. Yep. And also we need to look at this up here. So I'm going to duplicate that even as well. I think I can resize it maybe. Maybe not. Oh well, it's fine. So that's just so we can look at it at the same time here. So yeah, so let's go ahead and do this. So we already know how to read it, so this should not be too complicated, but we're going to do this very similar to how we did the other problem like this on the part C on the previous problem. So if you're in S0, then you're in this row, right? So there's going to be 2 arrows leaving there. There's going to be there's this arrow, and then also there's going to be this arrow. 2 arrows leaving S0, and one of them corresponds to the input 0, and one of them corresponds to the input 1. So they're easy to see what happens, right? This one is S0 to S1, and that's when the input is 0. Input 0. So this is input 0. And this is where you write the next state. So this is S0 to S1. So right here, we should put a S1. Okay. And then at the same time, you got to fill out here because this is also input 0. So there's 2 places corresponding to input 0. So this is input output. So the input is 0 and the output is 1. You put a 1 there. Okay. Now for the other arrow leaving S0, this one goes S0 to S2. So this is S2. And you just need to know what the output is, so you can write it right here. So this arrow, input 1, output 0. 0. Right? So that's it. So it's just every arrow is 1 column. So next row, for example, we're in, oops, I erased it. Next row is S1, so you're in S1. Again, there's 2 arrows that leave S1. There's one right there, and also there's one here. So one of them is input 0. This one's input 0. This one's input 1 from the 1. So the first one is S1 to S0. So you put an S0. And then input 0, output 1. So you put a 1 right here. Then this one is S1 to S3. So this is S3. And it says input 1, output 0. So that's a 0. So then you go to the next row, S2. S2 has 2 arrows leaving it. Find them. One's right there. One's right here. So you go S2 to S3 when the input is 0. So that's S2 to S3. And input 0, output 0. So that's here. The other arrow is S2 to S0. And input 1, output 0. So the output is 0. So we write a 0 right here. Last row. So we're in S3. S3 has 2 arrows leaving it. This one and this one. So this one right here is input 0. So we do this one first. S3 to S1. That's input 0, output 1. That's a 1. Then here we got S3 to S2. So that's S2. And input 1, output 1. So that's column 1, or second column, which is 4, 1. And we put a 1. All right. So that's how you do that. And that's our table. So that's our table. All right. So that, where did this come from? Oh, well. Um, oh, I see. When I moved it, I didn't pick up the bottom. Okay, cool. I don't know why I'm moving it. All right. So that's it. That's the end of the practice exam. And yeah, so good luck on the real exam. You can come for help on Thursday or Friday if you need it, and I will help you or send emails. And yeah, good luck. Turn in any late work that you have as well before end of Friday. I don't know if Canvas will be open after Friday, so you'd have to email me stuff after that. All right, so that's it.